Hi friends, welcome back. Today we're talking about parallelograms on the coordinate plane. And in a previous video, we talked about how parallelograms, the properties of parallelograms, and you're definitely going to want to grab your notebook and talk about those so that we can talk about those properties because that's going to apply here. Okay, so let's talk. For your notebook, here are the things that you will need. So for the first one, we have our distance formula here. Okay, and we use our distance formula to find the distance between 2 points on our coordinate plane. Now, you're going to want to remember congruent lines have the exact same distance, so that is why our coordinate plane is relevant, or our coordinate plane, our distance formula is relevant. Now, the other one that you want is our slope formula. And slope formula, remember, is y2 minus y1 over x2 minus x1. I just got a new document camera and it's focusing in and out, so I'm super sorry about that. Okay, so bear with me. Okay, so make sure that you've got those two things written down in your notebook. Now, there are three ways to prove a polygon is a parallelogram, or a quadrilateral. I should specify a quadrilateral. Three ways to prove that it is a parallelogram. You can do this by saying both pairs of opposite sides are congruent. You can do it by saying both pairs of opposite sides are parallel, or you can do this by saying one pair of opposite sides is both parallel and congruent, both parallel and congruent. So remember, we're going to use the distance formula to determine if lines are congruent, and then we are going to use the slope formula to determine if they're parallel. Remember, parallel lines have the exact same slope. They never cross, right? Okay, so that was my dance for you, just so that everybody's awake. All right, perfect. So with those properties of parallelograms, now what we're going to do is grab your notebook and let's give this a practice. We're going to, and I'm sorry if that's a little bit difficult to see here. Let's make sure I use a darker pen. Okay, so we have the, let's see. Okay, so we have these points right here, A, B, C, and D. A is negative 4, 3. So we're going to go over negative 4. 1, 2, 3, 4. Down 1, 2, 3. And we're going to call that guy A. B is negative 5, negative 3. Oh, whoops. A is negative 4, positive 3. Let's erase that. Okay, let's try that again. Negative 4, positive 3. 1, 2, 3, 4. 1, 2, 3. There's our A right there. B is negative 5, negative 3. So 1, 2, 3. And that is our B. And then our C is 6, 5. So we're going to go over, let me make sure this is a little straighter there. There we go. So we're going to go over 6 and up 5. So there's 3, 6, 1, 2, 3, 4, 5. Okay, and so we'll put point C there. And then for point D, we have 5, negative 1. So we're going to go over 2, 4, 5, down negative 1. That's point D. Okay, so looking at this, and of course we're going to use our straight edge when we connect things on our coordinate plane. And if you just have an index card, that's totally fine. I fold an index card and have to use my straight edge. Okay, so we're going to go ahead and connect these guys. And you know, looking at this on the coordinate plane, it looks like it's a parallelogram. So we could probably say that it is. However, if you have learned anything in geometry by now, it is that you can never assume anything. We don't assume anything. We are either told it or we have to prove it. So what we're going to do is we are going to use both our distance formula and our slope formula to determine one pair of lines is both parallel and congruent. So what we can do is we can use both, we can do two different points. We could do two different lines. We could do A, B, and C, D, or we can do A, C, and B, D. I'm just going to pick A, C, and B, D. So A, C, and B, D, and I'm going to rewrite these points here. So A is negative 4, 3, and C is 6, 5. B, D is negative 5, negative 4. D is 5, negative 1. So remember I said that you could do this three different ways. You could use just the distance formula and prove both pairs of opposite sides. So these guys are congruent and these guys are congruent. Or, like I said, you could do both pairs of opposite sides are parallel. So the slope of these two are the same and the slope of these two are the same. But for today, we're just going to do A, C, and B, D. We're going to prove that they are both congruent and that they are parallel. Okay, so for congruent, we need to first show the distance between A and C. So our distance formula, remember, is the square root of y2 minus y1 squared plus x2 minus x1 squared. You may see it also written as x2 minus x1 plus y2 minus y1 squared, both of those squared. That's fine because when we're adding, we can add in any order, so we can flip that around if we need to. Okay, for the distance formula, we're going to say if I call this my x1, y1, x2, y2, what we're going to do here is 5 minus 3. So we get 5 minus 3 squared plus this minus this. So 6 minus negative 4. 6 minus negative 4 squared. All right, when we do that, we get the square root of, oops, forgot my equal sign there. 5 minus 3 is 2 plus 6 plus, add the opposite, right? So 6 plus 10 equal 10 squared. So 2 squared is 4 and 10 squared is 100. So I have 104 as my distance formula. Now, this, you may remember simplifying your radicals. Whenever you have a radical that has a perfect square hidden in there, you can simplify that. And if you need to go back and look at previous videos for that, make sure you do that. But in this case, I can see that the square root of 4, which is a perfect square, is hidden in here because it turns out that if we multiply 4 times 26, we get 104. Now, looking at 26, I don't see another perfect square hidden in there because if I were to break that down, the only thing I have is 2 times 13, and both of those are prime, so there's no other perfect squares hidden in there. The square root of 4, remember, is 2. So the distance between A and C is 2 and root 26. Now, the next part that I'm going to do is the distance between B and D. So we are going to do those guys. The distance there is going to be, all right, we're going to do this minus this, so negative 1 minus negative 3 squared plus 5 minus negative 5 squared. Okay, so if I add the opposite, I get D equals 2 squared plus 10 squared. And this is starting to look familiar over here. We get distance equals the square root of 104. And again, we can simplify that to be 2 root 26. Okay, so far we have proven that both AC and BD are the same length. But what we need to prove is that they are also the same slope, because just because they're the same length doesn't mean that this is a parallelogram. So how do we prove that those guys are the same slope? In this case, what we do is we use our slope formula. So again, I have these points over here, and I'll do the slope formula over here so you can see. So for the slope formula for AC, I have 5, it's very similar to this distance formula. I'm basically finding the difference means subtract, between my x's and my y's. Y's on top. So 5 minus 3 over 6 minus negative 4. All right, if I simplify that and I add the opposite here, I end up with, I'm going to use a different red because that's a little bit too light there. So what I end up with is 2 over 10. Of course, we always reduce our fractions, so we get 1 over 5. 1 over 5. Let me use actually a darker pen there. That was a little too light. I'm sorry about that, folks. Okay, so that's AC. Our slope for AC is 1 over 5. BD now, again, we're going to find the difference in the y over the difference in the x. So we get negative 1 minus negative 3 over 5 minus negative 5. Add the opposite, I get 2 over 10, which again, this is starting to look familiar. That reduces to 1 over 5. So what I have done is proven that not only are these two lines, AC and BD, congruent, they are also parallel because they have the exact same slope. Hope that clears that up. If you have any questions, let your teacher know. Otherwise, great work, and we will see you next time.